All right, well, good afternoon, everyone. Welcome back to another exciting day in mathematics. Whoop, whoop. Warm-up 73 is on the screen, and it reads, get a die and a coin, then toss the die and flip the coin. Do that 6 times. Make a table, record the frequency. What are their probabilities? What kind of probability is this? If you don't have a coin, I think I have some over there in the top drawer of my desk. All right, let's get that going. Give you guys some time. Bag of dice are back here. Go. All right, send me your warm-up, see what you got. Code is on the screen. All right. Thank you very much. So, what kind of probability is this? Share with your neighbor, please. What kind of probability is this? Everyone? Empirical, yes. By now we should be experts at identifying which one is which. All right, copy the agenda for today. Warm-up number 73. Today we're moving on to multiplication rules of probability. Tonight's home play, pages 222, 223. Michael Jordan, the best. Numbers 2 to 8 evens only. What's that? Okay. Let's see, knock, knock. LeBron. Exactly. All right, so be nice, Mr. Q. Okay, my bad. All right. No. He's good. Congratulations to him and his achievements. So yeah. But once he has 2 3-peats, then we'll talk. Who has 2 3-peats?
I do. That's about it. You gotta do it this evening. Why are you laughing? It's true.
I'm not laughing. I'm just like, I'm smiling with a nice smile because, ooh, Larry Bird's good. Anyways. All right. So, with that said, last night's home play, make sure you turn that in on Canvas. Pages 206, 207, numbers 1 through 7 odds. And once again, tonight's home play, page 222, 223, numbers 2 to 8, evens only. All right? So get a Cornell note ready, please. And just for the record, by the way, I hear a lot of talk in regards to like records and all this and that, and somehow people keep forgetting about Kobe. What's going on? You know what I'm saying? Like they keep talking about all these people. Jordan, of course, Kareem Abdul-Jabbar, and all the greats, but they keep forgetting about Kobe, and he was out there, man. Anyways. Copy the objective, please. I can identify and compute the basic probability. We're still in basic probability. We're in the middle of that, the whole rules and such. All right, here we go. So yesterday we started using the addition rules. There were 2 of them. You did that. We still know that there's 3 basic probability areas: classical, empirical, and subjective. We know our definition. And then we talked about exclusive. We talked about the definition for exclusive. And then we talked about events in regards to mutually exclusive and not mutually exclusive. And we said mutually exclusive is when events cannot happen at the same time, and not mutually exclusive is when events can happen at the same time. Today we're going to be talking something similar to this. So again, I want you to write events, but on one side we're going to write independent, and on the other side we're going to write dependent. Events in regards to dependent and independent. Very similar ideas to what we did yesterday, but today we're just going to add a couple more things to it. So an independent set of events are when the event can occur without affecting the probability of one or another. They are independent kind of like this. Let's say you and your BFF. When you guys go and you leave campus and then each of you go to your home, I hope that whatever you do at home does not affect your BFF in their home, right? But now it's not really completely that the case, because some of you with technology, you can also affect your friends in their home. But if they didn't have technology and they were independent, whatever you did by yourself does not depend on what your BFF does by themselves. Is that correct? Yes? So you can go home and go wash cars just to be nice, right? And your BFF can go home and maybe make dinner just to be nice as well, right? Does that affect one another? No, not really. That's what we call independence, when events can occur without affecting the probability of another. So you remember the definition for dependent events. Very good. That occur affecting the probability of one another. So kind of like this. Let's say tomorrow we have a pop party. The probability of you guys doing well on that one is affected by how much you do your home plate throughout the week. Is one dependent on the other? Of course it is. And kind of like my Algebra 2 students, like yesterday I left them to memorize the, you guys remember, let's see, flashback to some of you, deriving the quadratic equation of a parabola. You guys remember that one? The whole process? Deriving, the whole process of deriving. So how is their grade going to be affected tomorrow if they didn't practice yesterday or today? You see what I'm saying? So that's a dependent, and we can get probabilities from all of that, okay? All right, we good? Yes, Mr. Q? All right, let's start with independent events by multiplication. Multiplication rule number 1. When two events are independent, the probability of both occurring is P of A and B equals to P of A times P of B. Copy that? All right. So once again, multiplication rules of probability for independent events is when two events are independent, the probability of both occurring is P of A and B equals to P of A times P of B. All right. Example 1 reads, a coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on a die. Bless you. Example 1, Q. A coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on a die. That was the purpose for the warm-up, so that you can at least be ready in regards to numbers. Okay? Once again, it reads, a coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 4 on a die. So let's do this one together. What would I write? P of what? Yeah, head and 4. Which means we need to have P of head times P of 4. So, what is the probability of getting heads? Tell your neighbor, please. Everyone? Yes? 1/2? 1 out of 2? What is probability of getting a 4, everyone? Therefore, the probability of both 1/12. All right, from 1 to 5, I'll come to 4. Do you agree with this so far? All right. So, let me move the screen. All right, so let me go back to the notes. All right, send me your notes, please. All right, copy example 1 super Q. It says, a card is drawn from a deck and replaced. Then a second card is drawn. Find the probability of getting a queen and then an ace. So copy the words. I'm going to leave this illustration here so you can use it as you write your probabilities. I'll give you some time for that. And go. All right, let's see what we got. So, they want to find the probability of getting a queen or an ace. So, get us started with writing our equation. What did you write? Who went last, by the way? Me? All right, Pedro, go. Probability of what? Queen and an ace. Okay. So that means, tell me what you write again. Okay. Pass someone so we can get some numbers there. Hold on. Now, this is reduced, yes? Do you guys see it? Because this should have been 4 over what, guys? 52 times 4 over 52. You don't think JC reduced at that point? We should be able to get the same answer, which is 1/169. And over here, you should have gotten 16 and is it 2704? Yes? And that reduced should give us that. All right, from 1 to 5, I'll come to borrow you with these. All right, so far so good. Send me your work really quick, please. Q. So for this one, don't copy the problem. Just write A, B, and C, and write me the probability for each of those situations. And it reads, example 1, make a Q. An urn contains 3 red balls, 2 blue balls, and 5 white balls. A ball is selected and its color noted. Then it is replaced. A second ball is selected and its color noted. Find the probability of each of these. A, selecting 2 blue balls. B, selecting 1 blue ball and a white ball. And C, selecting 1 red ball and a blue ball. So find me A, B, and C. Now, just let me note really quick, the fact that these are independent, look up to the screen. Let me go to the previous problem. All right. Flipping a coin and rolling a die, they're 2 different things, so therefore they are independent of each other. Agreed? In one deck, they're all together. However, what is the key word here, guys? Key word is replace, which means they put it back in the deck. Look at this one. What is the key word again? Replace. That means they replace back the ball inside of the jar or the urn, which means the probabilities again start all over. That's why these are independent. All right? Finish that up, please. Go. Talk it over to your neighbor before you finish off A, B, and C. All right, let's start with A. Selecting two blue balls. So I'm just going to write P of B and B. So, what were your, what was the probability for that, those events? Jet, go. 1 out of 25. Hands, have you got that? That is correct. Why? Because to select a blue ball, it's 2 out of what? What is the total? 10. So it's 2 out of 10 times 2 out of 10. That is 4 out of 100. And that gives us 1 out of 25. Okay. So far, so good. Let's go to part B. Part B, I'm going to write probability. Oh, sorry. Part B, I'm going to write probability of a blue and a white. A blue and a white. Tell your neighbor what you got for that one so Jet can pass it to someone. Jet, go. Who? Dom. What'd you get for B? 1 over 10. Hands, have you got that? Looks about right. Let's double check. Probability of a blue is 2 out of 10 times probability of a white. That's what? 5 out of 10, which is 10 out of 100. Take away some zeros. That's 1/10. That is correct. All right. And last, probability of a red and a blue. Share with your neighbor what you got, please, for that. So like that, Dom can pass it on. Dom, pick someone.
I got 3 out of 50.
3 out of 50. Hands, have you got that? All right, let's double check. Probability of a red one is 3 out of 10. Is that correct? Yes. Times of a blue one is 2 out of 10. So that is 6 out of 100. So if we reduce that, that is 3 out of 50. Ooh-wee. From 1 to 5, how comfortable are you with these? All right, and tell your neighbor once again what makes them independent, even though we're trying to pick two different things. What makes them independent? What's the key word that we're looking for, everyone? Yeah, replaced. Replaced. Okay. All right. After you send me your work, copy the next rule, rule number 2 for multiplication, and this is for dependent events. Dependent events. That's on the screen. Copy that. And it reads multiplication rule number 2. When two events are dependent, the probability of both occurring is P of A and B equals P of A times P of B dependent on A. That's just a symbol. It's a symbol. It's a bar saying dependent on A. It doesn't mean division. It just means B dependent on A. All right. As soon as you copy the rule, copy example number 2Q. It's on your screen, and it reads, the three cards are drawn from an ordinary deck and not replaced. Therefore, are these independent? No. That means when they don't replace something, that means that one event is dependent on the other. Find the probability of these events. A, getting 3 jacks. B, getting an ace, a king, and a queen in order. C, getting a club, a spade, and a heart in order. And D, getting 3 clubs. I forgot to bring that down. Getting 3 clubs. Copy that. All right. So I'm going to do with you A. And A is very, very similar to D. Okay, the challenging ones are going to be B and C, and I'll leave that to you so that you guys can talk it over. But let's go over A. And it reads, the probability of 3 cards are drawn from an ordinary deck and not replaced. Hence, keyword not replaced. Find the probability of these events. 3 jacks. Okay. Does everybody know the suits and all that? Yeah? Yes, Mr. Q. All right. So here we go. Let's get started. So we're going to write P of what? 3 jacks. All right. So who can give me the probability of the first jack being drawn? Everyone. 1 out of 13. All right. Let me write it first as a whole. 4 out of 52. Yes? Are there 4 jacks on the whole deck? Yes, here they are. 4 of them. Out of how many total cards? 52. There it is. But Mia said this is 1 out of 13. Yeah, because it can be reduced, yes? All right. Times 3 over 51. Tell your neighbor why 51 on the next one that they chose. What was the key word? Not replace. They got the card, they took it out, they didn't replace it on the deck. So, to illustrate, look up. This card, let's say, was this one I took out. How many cards do I have left? 51. So that means when I draw the next one, which would be this one, I'm left with 51 cards. Can we reduce that one, though? Yes? Yes, no, maybe so? All right. Zach, what's the reduction of that one? Very good. 1 out of 17. Next, tell your neighbor the probability of getting the third jack. The third jack. Everyone? 2 out of 50, or reduce to 1 out of 25. Everybody following? Yes? So this green one we got, let's say it was that one, we didn't replace it. We're left with 50 cards. That's why when we selected the next one, which was this one, we only had 50 cards. So that one is, let's say we got this one right there. That's that one. All right. So with that said, 1 times 1 times 1 is 1. 13 times 17 times 25. 5 what? Like that? All right. From 1 to 5, how comfortable are you with these? Did everybody understand the idea of not replacing something? Yes? All right. So for B and C, you pretty much start from scratch again with 52 cards, and then you try and find the probability of these. Work together with your neighbor just to make sure you talk out some of the kinks in your noodle. And I'll go ahead and stop the video right here for those of you that are following us. Like I said, today was multiplication rules, numbers 1 and 2 for dependent and independent. Have fun. Bye.